We're from North Carolina A&T. My name is Tiffany Smith.
I'm Asha Patrick.
I'm Camille Sherrill.
Donovan Sweet. Javon Rustin. And today we're going to be showing you two different ways to solve three different problems. We're going to show you two different algorithms, and then we're going to explain to you why we chose one algorithm over the other.
To begin, you have an if statement that assigns y to equal m and z to equal n if y is greater than z. If y is not greater than z, then z is assigned to m and y is assigned to n. In order to do the multiplication, there is an if statement that runs if y or x equals 0. If they do, the result is 0. If they do not, you set the answer to 0. Then have the loop run that runs n number of times. Then you calculate another value for the result, where the result will equal the result plus m. Then you have your answer.
In our first multiplying algorithm, we'll be multiplying y equals 3 and z equals 5. First, we'll check our y and z. If y is greater, m is equal to our y, and our n is equal to our z. But since it's not, our m will equal 5, and our n is 3. Next, we'll enter the loop. If either value were 0, our answer will be automatically 0. But since it's not, we set answer to 0, and then add our m value to our answer. And then we'll increment our count to 1. Next, we will go into the loop one more time and add our previous answer to 5 yet again. So our answer will be 10, and our count will be 2. We enter the loop one more time, and we add our answer 10 to our 5, giving us 15. Our count is now 3, which matches our n value, so we are at the end, and our answer is 15.
Here's another one.
To begin, you read in the numbers assigned to x and y. If x or y equals 0, then the answer is 0. If they do not, the result uses recursion to reach a final value with the equation x plus int times x times y minus 1.
Alright, I will be explaining the second multiply algorithm, in which we call the algorithm recursively. So in this example, we have the multiply algorithm, and we're going to use 5 and 4 as an example. So since neither of the integers are equal to 0, we're going to continue to the else statement, where we recursively call the multiply algorithm. And at first, our answer is going to be equal to the value of x, which is 5, plus, once we call it again, it's going to be x and y minus 1. So that algorithm will be, answer will be 5 plus, call it again, 3 minus 1. Answer equals 5, call it again, 2 minus 1, all the way until you get to 0. Once one of the numbers equals 0, then we return to 0. So once you return 0 right here, it goes back to this problem right here. So 5 plus 0 will give you a 5. You get that answer. It goes to the one above that. 5 plus 5 will get you a 10. Goes to the one right above that. 5 plus 10 gets you 15. Then right above that, 5 plus 15 gets you 20. And this is our final answer.
This algorithm will run faster because there are less ifs, and you don't have to worry about implementation of an extra variable.
To begin, you read in the numbers assigned y and z. Q is set to 0. Then there is an if statement that checks if y is greater than z. If it is, r equals y and n equals z. If not, r equals z and n equals y. While r is greater than n, the calculation of r minus n equals r will be performed. Then you will increment q. Once the loop runs, the result will equal q with a remainder of r.
I will be explaining the division algorithm. We'll be using the numbers 49 and 8. Since 49 is greater than 8, 49 is equal to r and 8 is equal to n. We subtract 8 from 49 to get 41. We increment q to 1 because that's the first subtraction. We then subtract 8 from 41 to get 33. Q is then 2. We subtract 8 from 33 to get 25, and then q is 3. We then subtract 8 from 25 to get 17, and q is then 4. Then we subtract 8 from 17 and get 9, and q is 5. And then for the last subtraction, we subtract 8 from 9 to get 1, and Q is 6. And because the remainder is 1 and Q is 6, the answer is 6 remainder 1.
To begin, you read in the numbers y and z and set variables x and q equal to 0. If y is greater than z, you assign y equal to m and z equal to n. If it is not, then you set z equal to m and y equal to n. While x is less than or equal to m, x's new value will be x plus n. Then you increment q. Then you calculate a new value for x where x equals n minus x minus n, and for q where w equals w minus 1. From those calculations, the result will equal q with a remainder of x.
For the second division algorithm, we have the numbers 45 and 6. Since 45 is greater than 6, we set 45 to m and 6 to n. 0 is less than 45, so we add 6 to get an answer of 6, and q is incremented to 1. We add 6 to get 12, and then q is equal to 2. We also add 12 and 6 together to get 18, and get q is equal to 3. Then we add 6 to 18 to get 24, and q is incremented to 4. We add 6 to 24 to get 30, and q is equal to 5. Then we add 6 to 30 to get 36, and q is equal to 6. We add 6 to 36 to get 42, q is equal to 7. We add 6 to 42 to get 48, and q is equal to 8. Because 42 is the last number that is less than 45, we subtract 42 from 45 to get 3. And we subtract 1 from 8 to get 7, and the answer is 7 remainder 3.
We picked algorithm 1 because it does not have the necessary ifs and the checkings. It goes right before and returns that value. Where here, it goes above and then has to step back down to be correct.
To begin, you assign variables to the numbers being computed. M will equal y and n will equal z. The if statement checks to see if the base m is 0. If it is, the answer is 0. Next is the else if statement that checks if the exponent equals 0. If so, the answer is 1. The else statement will set the result variable to 1. Then there is a loop that runs n amount of times. In each loop, the base number m is being multiplied by itself, then stored into result variables. Once the loop is finished, the calculated result is the answer.
In this algorithm, we will be raising m to the n power. We will set our m equal to our y and our n equal to our z. Since our m is not equal to 0, the answer will not be 0. And since our n is not equal to 0, the answer won't be 1. Then we enter the loop and we set answer equal to 1. Then we will multiply our answer by our m number, which is 3. So the first time we go through, we 1 times 3, which will give me 3, and count will be 1. The next time we'll multiply 3 times 3, and the answer is 9, and our count is 2. We multiply 9 times 3, we get 27, and our count is 3. We multiply 27 by 3, we get 81, and our count is 4. Since our count matches our n value, we are finished, and our final answer is 81.
We do it again, and we do it again.
To begin, you assign variables to the numbers being computed. M will equal y, and n will equal z. The if statement checks to see if the base m is 0. If it is, the answer is 0. Next is the else if statement that checks if the exponent equals 0. If so, the answer is 1. The else statement runs an equation that does the calculation of m to the nth power.
I'll be explaining the exponent algorithm, the second one, in which we call x and y. And in this example, x is going to be equal to 2, y is going to be equal to 3, and we're going to solve it in a manner in which x is going to be raised to the y power. We're going to set m equal to 3, n equal to 2, and since none of the integers are equal to 0, we're going to go ahead into the else statement, which is going to call the algorithm recursively. In our first call, we have 2 times the call the algorithm using 2 and 2. In the second one, we have 2 times the call the algorithm using 2 and 1. And our final one, we have 2 times the call the algorithm using 2 and 0. And since we have 0, we return an answer of 1, which will go back to the previous algorithm and return an answer of 2, which would then go back to the algorithm before that. And since we have 2 times that called integer, which is now 2, we're going to return 4. Go back to the final one before that, and we have 2 times the 4 that we just answered, and we return an 8. And 8 would be our final answer.
Algorithm 2 will be faster because this is in the main and this is recursive, which will run faster than the for loop on